Welcome, everyone, to what I believe is the 13th in our seminar tutorial series. This is the first one of 2021. We're excited to be back. Part of the reason it's the first one is there's been a lot of activity over here at Octoscope. Some of you may be aware that we are now a Spirent company, as you can see from the slides that we're showing. That's an exciting new direction for us. But it's important to also know that as a Spirent company, we remain Octoscope, and we still have our products and our commitment to our customers, and we still are looking forward to doing these seminars and helping people understand how to use the products. So things don't change from that point of view. That's why we are continuing to do what we've been doing. So today, the seminar title, as you can see, is Band Steering, Airtime Fairness, and Lies, Damn Lies. I'm not going to say any more about that, actually. I'm going to let you understand it as it unfolds. Quick introduction to who you're going to be hearing from today. First, there's me. I'm Lee Chinitz. I'm the Chief Technology Officer at Octoscope. I've been a fairly regular participant in these seminars, so those of you who have heard these before or watched them probably seen me, and you don't need to hear me talk much more. Part of the reason that you don't actually need to hear me talk is that for the first time, I think, in our series, we actually have an external presenter, someone not from Octoscope, and so we're pretty excited about that. We've got Tim Higgins, who is the editor of smallnetbuilder.com. He is very well known in the industry for doing tests and reviews of consumer Wi-Fi products. Been doing it for a long time. He's well regarded, well quoted, and you'll be hearing quite a bit from him later on in this presentation. So what I'm going to do is kick the conversation off with just a little bit of a laying the groundwork, and then Tim is going to take us through the real details and technical content. Before I do that, I'll make one comment, which is we do these seminars live for a reason. We actually do a couple of them every day, whenever we do them. And the reason that we do that is that we do like the interaction with the audience. So please feel free to ask questions. All right, so let's start off with the content for today. Those of you who've seen these seminars before, and really kind of any discussion about Wi-Fi testing or any sort of wireless testing, know that throughput is a very commonly used metric, probably the most commonly used metric when people are talking about the performance of the system. In our previous tutorials, we've done throughput where we connected stations and access points with minimum attenuation to see what the maximum throughput is that could be achieved. We've done tests where we've shown the throughput changing as a function of attenuation or distance between the station and the access point. We've shown tests where we've looked at the same kind of information while we actually rotated the device under test, the access point, in order to see the effect of orientation. And we did a lot of those tests in great detail. We have them all in our tutorial list. But one of the things that they have in common is that they were always a test between an access point as the device under test and a single station. The plot shown here actually is a classic rate versus range curve. So this is the throughput achieved in a single access point to station link function, in this case of the RSSI. But actually measuring throughput can be a lot more complicated than that. As I said, we kind of took the easy path and said, well, what if we have an access point in a single station? But in reality, and what people really are interested in testing, is what happens in a more realistic scenario where, for example, you have more than one station connected to an access point. And not only more than one station, what about more than one station and those stations are different, right? Maybe they're a modern 11AX station and then you've got a much older 11N station. What about when some of the stations are close and some of the stations are far? And what about when your device under test, your access point, has more than one channel that it can use? What does that look like? So for example, I'm showing that same rate versus range plot that I just showed on the previous slide here, except here I actually have 3 stations connected to my access point. You can see one's an 11N station, and that's got this low rate versus range curve at the bottom here. I've got an 11AC station, which is a little bit higher up, and then I've got an 11AX station, which is even higher than that. So my combined throughput is the red curve, and if I compare that combined throughput, which is the blue one in this plot, to the one on the previous page, which is the higher one, you can see that my combined throughput is actually lower. Is that bad? Does that mean that there's a problem? I mean, not really, because it's a different test, right? We're testing not just one station, but multiple stations. So what we're seeing there actually is just the effect of mixing fast and slow stations on a network. And I think people understand that if you mix a fast station and a slow station, you're going to slow down the network for everyone, but it may not be completely clear how big a problem that can be. It's actually, though, pretty easy to understand how big a problem that can be if you just do a very simple exercise, which I kind of walk through here. If you just imagine an access point that has 2 stations connected to it, one is fast and one is slow. So by fast, I mean that it can handle traffic at F megabits per second, and the slow one can only handle traffic at S megabits per second. And let's say both of them have to send the same amount of traffic, which is M megabits. So it's going to take the fast one M over F seconds to send that, and it's going to take the slow one M over S. So the total traffic sent is going to then be 2M, and the data rate then would be 2M over the time, which is the sum of the fast time and the slow time that's shown here. If you just, cancel out the M's because they don't matter anymore, you can see that the average throughput in this case is 2 times this ratio, which is based on 1 over the fast distance and 1 over the time and 1 over the slow rate. By the way, this is known as the harmonic mean, and you can feel free to read about it many places, but Wikipedia's got a nice little entry on it. So what that shows you, if you kind of think through it, is that the slow devices really dominate the network speed. Again, if you take that little equation and you just do the little exercise of saying, well, what if my fast speed is just infinitely fast? I can just send bits, an infinite number of megabits per second. Then my 1 over F term will disappear, and this whole thing will reduce to twice the slow speed. So no matter how fast your fast devices are, if you have a fast device and a slow device, the best you can do is an average throughput of twice the slow device speed. So that really gives you a sense, and this little graphic up here is intended to show why that is. The reason is that since it takes the slow devices so much longer to send their traffic, they just get more time on the air, or they need more time on the air. So the fast devices are sending their things and getting off quickly. The slow devices are sending for a very long time. So they essentially dominate airtime. If you look back at our tutorial number 10, you'll see we have a discussion of what we call bad apples in that case. But actually that's a little bit judgmental if you think about it. Is it really a bad apple? I mean, it's not that it's bad, right? It's just slow and old. And so many of us are getting slower and older. So, I don't really want to judge here, but that does raise a question of, from an access point of view, how should it actually address having these kinds of stations on the air? What is the right strategy? Maybe allowing all the devices all the time they need is not really the best strategy, but what is the best strategy? I'm going to take just less than a minute to relate this whole discussion, by the way, to something outside the whole realm of Wi-Fi and communications. This is exactly the same story as to why, for example, if you were to go biking and bike uphill and downhill, your speed is actually determined by how quickly you can handle the uphill parts. The downhill parts, even if you can bike infinitely fast downhill, don't really matter as much as all of the time that it takes you to bike uphill. So if you want to increase your biking speed, the important thing is to make sure that you can increase your uphill speed, or the slow part, or of course only bike downhill, actually my preferred solution. So if we go back to that question then of what is the best strategy, we're actually heading into the realm of what people refer to as airtime fairness, right? So it would be a good idea then for the AP to handle, treat things fairly. But that hasn't really helped because we haven't actually defined what it means, and we've just moved the question to a new word, right, which is fair. So what's fair, right? Should all the devices get all the time they need? Well, we know what that leads to. Maybe the AP should only let the devices get the same amount of time. Would that be more fair? I mean, possibly. And what we're showing here is you can actually do a similar kind of intellectual exercise and say, well, what are the choices the AP has, right? If we take a fixed amount of time then and say, how should the AP divide up that time? You can say, well, it's going to give it, some amount of time for the slow user, which we call ST, some amount of time for the fast user, which would be the total time minus ST. And then the total bits will be represented this way, right? It's just the fast data rate and slow data rate times their time. And then the throughput is that number of bits divided by the time, which is T, which you can play around with and reduce to something like this. And what you can see is that you end up with essentially a linear plot that tells you something you kind of already knew, which is if you give all the time to the fast users, then the throughput that you get will be the fast speed. If you give all the time to the slow users, then the throughput that you get will be the slow speed. And it's just essentially a linear choice between that as you start to apportion a certain amount of time to the fast and a certain amount of time to the slow. So, if an access point is just gaming the system and just saying, well, I always want to win on throughput, well, clearly the best thing to do is to pick a fast user, don't let anybody else use the channel, and just let that guy send traffic, and then your throughput will be the fast speed, right? But of course, that's not fair either. So it's a complicated story, right? It's a complicated thing to figure out. How should the channel be apportioned? It's even more complicated when the AP has more than one channel to choose from. Now it has to decide a number of things, not only how it's going to split up a single channel, but how it wants to move or at least allocate users to different channels. This brings us to the realm of either band steering of the multiple bands or load balancing. There may not be multiple bands, but at least different channels. So now the question that the DUT has to put to itself is, what do I do? Do I put everyone on the fast lane? Do I put slow guys in the slow lane and fast guys in the fast lane? Is it right to only think about, their supposed speeds? Maybe I should think about other things like how much traffic they're sending. So there's a lot of questions to choose from. So the table that I'm trying to set here for Tim is to just make it very clear that making the best use of the capacity of an access point is a pretty complicated question. There's a certain amount of total capacity, and then it has to divide it up, right? There's a bunch of channels. It needs to decide how to decide which users should be on which channels. Should that be based on whether they're fast or slow, how much traffic they're sending? Maybe some are, high priority traffic. Is it some complicated mix of those? And then even within a given channel, what do you do when some are fast and some are slow? And worse than that, the AP doesn't really have complete control. The way I just kind of laid that out, it makes it sound like the AP can do whatever it wants, right? Once it has its own decision, it can say, great, I'm going to take fast users and put them there, slow users and put them there. I'm going to allocate this much to my fast and this much to my slow, and I'm all set. Well, that works if the stations let you do that. But in Wi-Fi, as I'm sure many of you know, the stations don't actually have to listen to what the AP says. Over the years, Wi-Fi has become better and better at making it possible for the infrastructure side to indicate to the stations what it would like them to do and what it thinks a good idea would be. But the stations may not have the ability to either understand those messages or the interest in actually paying attention to those messages. So the stations can be basically as stubborn as they want, and that will limit the degree to which the AP can kind of make those decisions. So with that being said, I'm going to turn this over to Tim now to show you how he took a crack at looking at these kind of problems.
Hi, everybody. I had a one bullet point to lead slide, but I'm Tim Higgins, the guy who runs SmallNet Builder. I don't know about talking about old and slow, but I'm at least one of those. I've spent the first part of my career building big iron mixed signal test systems for a lot of the companies that I deal with now, but concentrating on semiconductor test. Second part of my career, I've been testing and reviewing consumer networking gear, a lot of which in the Wi-Fi area. And basically, I've been in the consumer Wi-Fi game since the very beginning. The very first Wi-Fi routers fell under my testing hand. And we talk about a game, it's basically been my business and my career for the past 20 years, but it is quite a game and gets exciting at times. But the main part of the game is the game of numbers. And you can choose your number, but you always want it to be big. And we look at this selection of different numbers I pulled off of product boxes. And some cases the manufacturer will add up maximum link rates. In other cases, they'll count the streams. And some talk about coverage, although that's not as commonly done. Mostly it's in link rates and streams. But the biggest game is now has moved from just talking about throughput and putting it in now the concept of total throughput or total aggregate throughput, which basically says you're dealing with multiple stations. Why are we dealing with multiple stations? Well, this one survey that I pulled off the internet says that the average household now has 10 connected devices. Your household may have more, it may have fewer, but going down the list, you can see a couple of mobile, couple of phones, couple of computers, a smart TV, a tablet or two, and then going down the list. And if you have your 0.08 virtual reality device, I don't think it's taken too much bandwidth, but it's there. But you could see that 10 devices isn't out of the realm, and maybe half of those are simultaneously active at any given time. Another view of this, talking about a busy Wi-Fi household, and this comes from a recent white paper from a well-known manufacturer of networking devices, both Wi-Fi and cellular. And they talk about a busy Wi-Fi household having 4 high-quality video calls, 4 multiplayer gaming sessions, 5 security cameras, 3 people browsing the internet, and background traffic of a couple people doing large file uploads, only 1 person doing email, apparently not work-related, and then 4 neighboring networks that are trying to use your bandwidth to the 250 megabits a second. So this may be your case, but it's another whack at defining what a Wi-Fi household is today. But the thing in common is that it's basically dealing with multiple devices. So if the world has gone that way, it looks like we better test that way. And in the consumer reviewers, we're generally a limited lot. We don't have a lot of, I'm very fortunate to have a test system as powerful as the Octoscope test system, and I've had good test partners over the years. But basically, you're going to have to deal with doing multiple stations. And if you have multiple stations, at least for me, I need to be able to automate it. I always forget when I have multiple things to do something, and I'm at the end of a couple-hour test process, and then, I forgot to associate that client. So I have to automate it. You also want to have as much control over the station behavior as possible. Why is that? Why do I say station behavior? Because most of what I test are routers and APs. And I don't know what their design behavior is, so I have to know what the station's behavior. It's my test instrument. The stations are my test instruments. I want to know as much about them and be able to control as much about them as possible. Multi-station, what's the definition of multi? Well, you want a bunch, and that's basically as many as you can afford or reasonably deal with. And we'll see what we have to deal with on the octoscope system in a little bit. Let's talk about Smart Connect. Smart Connect, if we're talking about multiple devices, you're going to be talking about Smart Connect. And Smart Connect, the term Smart Connect came into being many years ago when the first tri-radio routers were introduced by Broadcom. And that started out as Broadcom's counter punch to multi-user MIMO. But now it's really evolved into a commonly used marketing term for band steering. So in the consumer world, you'll see everybody talking about Smart Connect. That's one of the features on the product boxes, and basically they're talking about band steering. Now, we promised you lies in the teaser to this seminar, and the main lie, and if you want to be nice about it, the marketing magic, is that the big lie is that your router will always be able to guide your device to the best AP and mesh mode. And I like to think of this as the Wi-Fi maitre d'. He's going to make sure that you get seated at the Wi-Fi table that gives you the most bandwidth, the best connection, so that you can feast, your devices can feast to their heart's delight. And what's the best? Well, when you're dealing with best, you're talking about fast stations, and fast stations are generally going to connect, will be seated at the 5 gigahertz table, and slow stations are going to be sit over near the kitchen and where the 2.4 gig table is. But the truth is, as Lee pointed out, and his little reluctant station, is that the APs can try to influence the connection, but the station ultimately decides, because that's the way the Wi-Fi is designed. All right, moving right along, it's demo time. So what are we going to do with the demo? If you've been a fan of these tutorials, you've probably seen this diagram before. The system I'm going to be using for the demo is the Octoscope Stack Max. It's a very capable system. It can do mesh disting. It can do multiple device. It can have stations, both the PAL devices and real devices. But I'm going to be using just a very small part of this box, and it's this part here. And basically, the device under test is going to go in the big box. That's a smart box, a couple of attenuators, and then connected to the PAL box. And the PAL box is where all the magic happens, at least for this demo. Now, the PAL box, if you're not familiar with it, consists of 16 real test devices. So each is individually controllable. They are all based on the Intel AX200 Wi-Fi 6 radio, and 12 of those stations are hosted on Ubuntu Linux, and 4 of them are based on Windows 10. So you get a little bit of an ability to see the difference in drivers capability between Windows and Linux. Each of those 16 stations are grouped into 4 groups of 4. And each group of 4 is connected to the same pair of high gain antennas that are situated in the 4 corners of the box. And I'll have a picture of this in a little bit. But basically, you have the spatial diversity so that if the device under test, the AP under test has MU-MIMO capability, that should be able to come into play. So we'll come back and look at this to see what part of this we're going to use in a second. Oh, and by the way, not shown in this diagram are the attenuators between the groups of 4. So basically, there's an attenuator channel behind each of these antennas. So each of the groups of 4 can be set at a different distance, have a different path loss introduced. So you can play with that. It's another factor in the test. The goal of this demo is to basically see how well a consumer router optimizes throughput for a station mix. Our working assumption is, as I said before, is that fast stations are going to be connected to the 5 gigahertz radio. Slow stations are going to connect to the 2.4 gig radio. But as Leah said, the problem is deciding which is which. It's not an easy job. The AP has to deal with RSSI, can make the decisions based on RSSI, link rate, signal quality, device type, radio congestion, and other things. And of course, the stations have their own ideas about where they want to connect. A little reluctant station. Here's a peek behind the curtain. One manufacturer, ASUS, has decided that they actually unveil the controls for Smart Connect, and this is for their tri-band router. And it's pretty obvious how you're supposed to set these controls. They're very easy to deal with. You can see that they're grouped into a trigger condition, which is where the device will be, the point of which will be steered, the station selection policy. So this is when you roam, and this is where you're going to roam to, or how you're going to assign the devices to. And then the mysterious interface select and qualify procedures, which look like they have a couple of target bands and bandwidth utilization controls. And this VHT selector basically lets you say only AC devices or only AX devices are allowed to connect to this particular radio. And there's the final group here is a bounce detect, which keeps stations from once they've decided, make them stay at the table that they connect to. And the real question is, if you're going to mess with this, which nodes are you going to tweak? And how are you going to break it? Generally, I don't mess with them. And that's the general rule is that since I believe the manufacturers in their infinite wisdom know how to present their products in the best way, I give them that opportunity. So I usually make very few changes to the out-of-the-box configurations for routers when I test them. So what are we going to do in this demo? In this demo, out of the 16 state pals, I'm only going to use 4 of them. And this actually turns out to be, you can reveal a lot about a router from just using 4 stations. And going from the bottom right counterclockwise, we're going from, there's basically 4 flavors of stations. The most capable is a 2-stream Wi-Fi 6. The next most capable is a single stream Wi-Fi 5. And then going to a dual stream Wi-Fi 4, 802.11n, and finally a single stream 802.11 device. And again, these are in different attenuator groups, so I can set each of these at a different distance from the device under test, so that should I choose to do that. And actually, I will choose to do that. That's part of the demo. If we look at what we have, best case throughput scenario, what I did here is I associated each of the station types to a 5 gig radio on the device under test to see what's the best throughput I could get. You can see the numbers. You can see that every radio we're allowed to get its best throughput. Each station we're allowed to get its best throughput. You'd see about 1.7 gigabits of total throughput. And you can see from the link rates below, we're at they're able to achieve the maximum link rates with no attenuation put in between. And the link rates range from 1200 or 1201 down to 150 megabits a second for the single stream end. You notice that this is greater than a gigabit a second, which is most of the ports on consumer routers are gigabit ports. But fortunately, the product that we're testing has, and the industry has now moved to add 2.5 gig Ethernet port, or in some cases, a 10 gig port to a router, but usually it's only one. And right now you have to, it's either dedicated to the WAN port or you are able to switch it between WAN and LAN. For this test, I'm configuring the 2.5 gig port on the AP under test on the LAN side, and all the testing is done on the WAN side. So I'm not doing any testing through WAN to LAN. Okay, so what's the test? The test is I basically use the scripting capability of the octoscope system. It's a Python script that uses the octoscope API. I do something very simple. I basically associate stations one by one. So I associate the first station, let's take the Wi-Fi 6. I wait 10 seconds. And I wait 10 seconds to see if there's to allow any post-association band steering to occur. And then poll each associated station for channel and BSS. So I want to see where they went, what channel and what actual radio. The BSS tells me what particular radio I will have. So this is not so, the BSS isn't much of a question when you're dealing with a single point router, but using this test in a mesh configuration, you have lots of radios involved, and you want to know which one your device connected to. And then I wait 10 seconds after I do the poll, and then I repeat the loop. So we're associating a new device about every 20 to 30 seconds, because it takes time for the devices to associate. And I do poll all the devices in each loop, so I'm able to see whether or not they change channel at some point during the test. So if the router decides, oh, I've got too much load on one radio and I need to move somebody to another radio, I can detect that in this test. Here's the device under test. It's all revealed. It's an ASUS top-of-the-line GT-AX11000. It's a tri-radio router, Wi-Fi 6. It's not the 6E version. It's the 6 version. ASUS also has the AXE11000. The way I've configured the radios is that the 2.4 gig is set to channel 6, 40 megahertz bandwidth. The 5 gig is on, first 5 gig radio is on channel 36, and the high band Muni 3 radio is up on channel 149. I'm using 80 megahertz bandwidth. I don't want to deal with DFS and the associated delays and uncertainty that come with it. I am using 40 megahertz on 2.4. And so these are the maximum link rates that an AX device can achieve. All right, so these are 2 stream rates, because we have 2 stream devices. For the first demo, I'm going to take each of the 4 stations. So again, we have the 4 different station types, and I'm going to park them all right next to the router. So no attenuation, give them the best signal possible, and see what they do. To do that, I'm going to bring up so this is the script manager. This is the heart of the recently introduced script machine. Octoscope has announced it, I think, fairly recently. And what it is basically the controller for the scripts. Those of you who have bemoaned the fact that some don't like editing config files, text config files, you don't have to do it with this. The script manager lets you configure scripts, a series of scripts. You can duplicate them, you can loop them, you can move them around in terms of order. You can stop on any test. So it has a lot of features. And if you want to change parameters, you basically can go in and can have also multiple config files. And the config files are in JSON format. So for example, you can open up the parameters for this test. And these are set by the program writer. These are not built into the system, but basically, if you set up your program right, just by changing the elements in the config file, which are all editable from here, you can change the behavior of the program, of the script. So I'm using the same basic script, and by using different config files, I'm configuring the devices to do different things. So the first station, as I said, we're going to do the 4 streams. 4 stations all parked right next to the router. So without further ado, let's run the scripts. So this, what we're able to do here is watch both the throughput view, and I can also, the console window just lets you know what the script is doing. So the first station is being associated, and you notice that I see where the station associates. And this is using the real-time status capability that Octoscope has in the system. So first station associated channel 36, and it's got a pretty good throughput. Again, this is the dual stream AX device. So this is sort of the best candidate. So it's the fastest of the fast. So you can see I'm printing out the channel and also the DSS that the device connects to. And so I waited a little bit, and now I'm associating the second station, and that station has now gone to channel 149. So the router so far has made a good decision in that it's got 2 5 gig radios and said, oh, I've got 2 fairly fast capable devices, so I'm going to assign each of them a different radio. And so our throughput has gone up to about 1.3 gig. So now I'm in the loop where the post association, the post poll, and now I associated the next station, and this is the dual stream 11N station. So it's a little bit slower, It's got a maximum link rate of, 300, I think I said. So it's associated, and it has gone to channel 36. So the router has not decided to put it on 2.4 gig radio. As a result, since a fairly slow station and a fast station are sharing the same radio, you can see that the fast station took a throughput hit. It's not as bad as it has been in the past. You can see that it's not brought down really to its knees. So there may be some airtime fairness baked into the router that's at play here. But you did get an overall throughput hit. So whoever's sitting on the first station might not be happy if they were using this much throughput. Now again, a single device using 900 megabits of throughput is not realistic, but for the purposes of this demo, I want to keep the channel loaded. And finally, the last device, and this is the single stream N device, so it's the slowest device, and that radio that is also associated to channel 36. So in this case, 3 devices ended up associated to one radio, and nobody got associated to 2.4. So that's we can infer from this that the router, at least in this case, has made its steering decisions based upon, looks like, based upon primarily signal strength. So I'm going to clip this, stick it here, so we can keep track of it. Oopsie. Oh, I gotta do it again. So we're going to put him here. And as I said, we ended up with what? We ended up with 36.149 and 36.36. So we're just going to record that. Okay. Moving on. The next station is we're going to take those same 4 stations and stick them fairly far away from the router with 45 dB attenuation. So to do that, I uncheck that box, check that box, and run the script again. So in this case, since everybody is what I would say, I would classify as slow, because you're having devices parked fairly far away. And again, the RSSIs are going to be in the like -70, -80. I would expect the devices to be connected to channel, everybody get connected to the 2.4 gig. And in fact, the first station, the AX dual stream AX station, did get connected to channel 6. So it did get connected to the 2.4 radio. We'll see if that continues. Now again, these are the same stations. All we did is just move them away from the router, move them away from the AP. So you can see that you can have an AX, a dual stream AX station, move it far away, and its throughput drops. Now you're still getting 250 megabits a second of throughput, which isn't too bad, and it's still very usable. But it's certainly not the 900 or so that we had before. All right, next station associated. This is the single stream AC. Again, sitting at -45 with 45 dB of attenuation, and it also was added to channel 6. So in this case, we're seeing that the total throughput, again, they're not dropped, they're not tracking each other totally, and the throughput did not cut in half. So we've got some mechanism in place here that's helping keep the throughput up.
Hey Tim, so I have a question. I know that you said you would expect these to go to channel 6.
Yep.
And I guess we're still in the process of watching what's happening, but it does look like they're all going to channel 6.
Mm-hmm.
You don't find it surprising that the AP would leave 2 perfectly good 5 gigahertz channels unused, or do you think it's just because since it can't predict what's going to happen in the future, it wants to reserve them.
Yeah, no, I don't think it's that smart. I mean, I've tested so many of these that whenever somebody says they've got something smart, my antenna go up, and I usually try to poke at that a lot. I don't think the router is that smart to sort of say, oh no, I'm going to conserve some bandwidth. I think it's making the decision primarily based upon, as I said, signal level, and since these are relatively low signal levels, they're considered slow. I mean, if you've got a device, no matter how good it is, that's sitting at, with 45 dB attenuation, sitting at sort of -80, -70. Although that's a typically -70-ish is a roaming trigger point. No, I guess I'm not surprised by it. I pretty much expected that and all 4 stations have gone to 6. So
there are a couple of questions, by the way. So one I think answered, but our friend Craig Smith is around. So hello to Craig. And he asked, is the 2.4 gig channel 20 or 40 megahertz? It was 40 megahertz, correct?
40, yeah.
And then we have another question on the chat. The question is, or it's more of an observation. It seems like load balancing is not happening. Is the observation?
Well, let's see. Define load balancing. I mean, the fact that I've got a channel being loaded and I should go to someplace else, or how would you recognize load balancing? I guess would be my question. How do you define load balancing?
So the response is another radio.
Yeah.
Maybe it's very similar to the comment that the observation I made, right? That it is not balanced. It has a certain load.
Yep.
And it's not balancing that load. It seems to be making a very simplistic decision of, this is a slow guy, so it goes on a slow radio, and I'm not going to balance my load, right?
Right. Yeah, that's a fair observation. Everybody ended up on channel 6, so the router didn't take it. Like you said, there's 2 perfectly good, very capable 5 gigahertz radios sitting there unused. Now, perhaps I've run these tests for a while. While I'm yapping here, let me start another test so that I don't have to have too much snappy patter. This case now is I'm going to mix things up in terms of attenuation. Same 4 flavors of stations, but now I'm taking the fastest one, and sticking it at closest to the router. The AC, single stream AC, I'm using 15 dB increments here, and just moving each station successively further away, right? And that's this one. And so this is a good one in that now we have a mix of attenuations and capabilities. So anybody want to guess where things go? I think the first one's a gimme. I think the first one is pretty much, it's going to go to one of the 5 gig radios. But we'll see whether 15 dB of attenuation makes any difference for the second.
Craig is asking mean question. Has someone tried to compare the measured throughput against what the theoretical harmonic mean should be in these multi-station tests? Seems you'd also need to include an overhead factor for multi at the same speed that aren't accounted for by the harmonic mean equation. Yeah, I don't think, no, we did not do that.
No, I have not done that in this demo.
I think what we did,
is the question getting at whether some kind of airtime fairness is done? Because if airtime fairness is not done, then you'd hit the harmonic mean, right?
Yeah.
All right, so now we have our first instance of 2 radios, 2 fairly fast devices, and now each one got assigned to a different 5 gig radio. So the first, so one's assigned to channel 36, one's assigned to channel 149, and as a result, we have a nice bump in throughput up to 1.3. But we've seen this before. We saw this in the first case where initially we went up. So the question is anybody else going to get assigned to a 5 gig radio? And nope, next one got now is assigned to channel 6. So the dual stream N radio is now assigned to 6. But actually, this is a good thing because now we have one device assigned to each radio. So all 3 radios are busy. The router seems to be making more intelligent decisions about load share or band steering. Sorry.
You're getting really close to your.
Putting the load, right? So now we're at 1.6-ish.
Yeah, you're getting very close to your max, right? Your prediction was 1.69, right?
1.7, yeah, about 1.7. So yeah, it's pretty close. But something's going to give at this next one because we got 3 radios and now we're out of radios to have everybody be happy and alone. So where do we think the last one's going to go? Actually, we know where it went because it went to channel 6. So the slowest station went to channel 6, and so this is sort of the ideal, at least in this scenario, because we have this first one went to 36, most capable. The next most capable station also went to a separate 5 gig radio, and then the slower stations went to channel 6. So this is, I would call this a good outcome, an intelligent outcome, that the router made good decisions this time. But, why it made those decisions, again, there's nothing particularly magic about the attenuations that I chose. All we know is that I did mix up device type, so capability and attenuations. But this is, the router was able to maximize its throughput in this particular case. All right. The last case we've got, I want to move right along since we don't run out over time, is I'm now going to take I'm going to change it up and make every one of the stations a best case fastest station. So I have 4 dual stream AX stations and they're parked right next to the router. So we're going to see what this comes up with. Now, what would you like to see in this case, right? Well, we know that if everybody gets added to one radio, then the bandwidth is going to get split. So the individual throughput will take a hit. We don't have 4 or 5 gig radios to deal with. There's also a scenario, and I've seen this because I've run this actually in the article that this tutorial is based on. I've run all 16 state pals, and it's very interesting what happens as the later ones associate, because you really reach a point of diminishing returns in terms of maximum throughput, and so you can watch the total throughput, but what ends up happening to the individual stations is interesting. And I've got, the article has lots of analysis. I cut the data a bunch of different ways to try to, see what was going on, to see whether, fast devices always got assigned to the 5 gig channels. And it pretty much turned out that if you have a really slow station, that most of the time they would get directed to the 2.4 gig radios.
So what happens? Craig's had a question for you that is maybe related to what you're just saying. He's wondering, does it seem like the decisions are based only on the RSSI? So if you did the one that you did before, where you had the most capable station, also the closest, what if you had reversed the station capability? Would the total throughput have been much, much lower? That is, would the slow guy, even if you had a one stream 11N guy, if he's the closest, mm-hmm. would it have still put that, at 5 and put the AX guy, down at 2.4?
I haven't run that scenario, but the script is capable of controlling you can set each station individually, so you can. The only thing that you're limited in is that within a group of 4, you only have one attenuation setting. But each of the stations can be set differently, and also the script can be changed to control the order in which things associate.
And another question came in, which I think is the same. I'm going to read it anyway and see if you hear it differently, but I think it's the same question, Carlos. Carlos asked, what if the most capable stations had the 30 and 45 dB attenuations instead of the slowest ones? Isn't radio assignment purely done based on station RSSI? I think that's the same question that Craig just asked.
I mean, it sure looks like it. But we did have a case, we had the case in which all of the, the stations were the same, but just everybody got parked at 45, right? So 45 dB away. Now, although not only, it wasn't, we didn't spread it around, but, if we go back to this case where everybody was 45 dB, the router certainly had the opportunity to take the most capable station and assign it to a 5 gig radio, and it didn't. Right, and that's just
I think his point was, well, isn't it done based on RSSI?
Yeah,
so
which makes it look like yes in this case, right?
Yes,
it's
like, makes it look like
whatever.
Yes. Yeah, and that was
maybe your first test is an interesting one to look at, because there I think you had 3 on 36 and 1 on 149, even though they were all on great.
Yeah.
RSSI.
That one ran into a little bit of a problem. But so far in this test, I've had to restart the test. Looks like somebody got unhappy. Maybe the router's getting cranky because we keep changing things up on it so much. But at least so far in the last scenario is that we had one station associated to one radio and went to the second one went to the other radio. The real question is what happened. Now notice that, by the way, with the 2 AX stations, when our throughput now is up at, north of 1.8. So AX stations, in fact, a single AX station, dual stream AX station, was able to go at 900 megabits a second. Again, this is running full tilt TCP/IP. The old rule of thumb where we say, oh, you take your maximum link rate and sort of 50% of that, it's not true anymore, right? It's really, these stations are, the protocols and the packet aggregations have gotten really much more efficient. So you can just about with a single station, if you're able to run a full blast, a single dual stream AX station, pretty much max out a gigabit Ethernet port. So you really do want a 2.5 gig port, or at least a 2.5 gig port on a tri-radio router. And in the article, I showed, what happens. I actually had 2 tri-radio products. Both happened to be ASUS, but one had a gigabit Ethernet, only had a gigabit Ethernet port. The other had a 2.5, and you could basically see the flatlining limitation of the gigabit Ethernet port.
Can you see what channels it's using?
Yeah, sorry. Yep. So far, 36 and 149, which is, you can basically infer that from the throughput, because it went up high.
Yes, unless it was really good multi-user.
Unless, really good multi-user MIMO. So the third station is now associated to 149. Now, we'd expect it, because we now have 2 radios sharing a connection, that we're going to get a throughput hit, but we don't. We actually, the throughput continues to climb, and now we're north of 2 gig. And that is basically got to be, I think, some MU MIMO at play.
Nice. So the MU MIMO gain here is what is looks like about 300, maybe 400.
Yeah, but it's still going up. The last station now is being associated, and we'll see whether or not we split it and it goes to 36. And nope.
Tim, remind us, the AP here is what is that? That's a 4x4, right?
Yeah, it's a 4x4.
And so the stations are 2x2, so
correct.
That's why we're getting MU MIMO gains with 2 stations in a single radio.
So the last station the router did not split things accordingly, and so we ended up with 3 stations on 149. That last station, You do see a throughput, a little bit of a throughput drop, because now you have 3 stations sharing it, but you didn't get a real big drop in total throughput. In the best case here, the router should have taken 2 stations to 36 and 2 stations to 149, but it didn't do that. So in this case, we ended up with 36. 149 and 149. Let's do a clip. So we have 4 scenarios, 4 different results. And we do see that when you have 4 very fast devices, then the router can really come up with an awful lot of throughput. I mean, this is pretty amazing how much throughput you can get out of this. And again, this is just four stations running full blast. Now, of course, when you get more stations involved, now things get airtime management gets much trickier, and the router has to deal with a lot more variables. But you can see we've gone from in case 1. First case, we topped out at over about 1.3, but then dropped as further stations came online because less capable stations were again sharing radios. This is a case in which we had 3 radios sharing the same, 3 stations sharing the same radio, but we didn't get 1.8 gig of throughput. In this case, we have everybody at 45, fairly low throughput, but again, no utilization of 2 of the 3 radios in the product. In this station, all 3 radios got used, fairly good allocation of and logical allocation of radios. And in the final case here, where faced with an embarrassment of riches in terms of stations, it didn't do a perfect job, but still got a pretty good amount of throughput out of the router. Sort of the final thoughts is it's not that Smart Connect is dumb, but band steering is a pretty difficult job. Again, defining fast and slow is difficult. I'm glad I don't have to do it. I'm also glad I'm not the guy or the person that is writing the airtime scheduler for these products, because we didn't even talk about OFDMA and MIMO and airtime fairness and all the other different things that come that the airtime the scheduler, and also traffic. We gave it a fairly easy traffic load of just full blast. It was all. We can also see that optimizing total throughput, you might not optimize the individual station throughput, because eventually you run out of radios. There's only so much you can do with a limited number of radios. Now, mesh systems, you have more radios, but then you have the loss of backhaul bandwidth in the backhaul. So although you have more radios, unless you have a Ethernet backhaul, which to me is not a mesh system, that's a classic AP, multi-AP system, then you can reach diminishing returns. At this point, I'm going to hand it back to Lou.
All right. Tim just said a couple of things. So first of all, there's a lot of information that was just presented, but even more information in the article that was posted at smallnetbuilder.com called "How Much Total Throughput Can Your Wi-Fi Router Really Provide?" So definitely go there and take a look at that for a lot more detail. Tim actually just made a comment, we didn't get into even OFDMA and multi-user MIMO. Just for those of you who may not have seen all of our tutorials, we do actually tutorials that touch on both of those topics. So anyone who's got interest in those, please take a look through. I have a list later of our tutorial links, and they're all available at our website, which is still octoscope.com. So just in quick summary, one of the things you'll notice if you were to take a look at the article at smallnetbuilder.com, you'll see that Tim points out that the situation actually is a lot better than it used to be. He's been looking at these kinds of things for quite a while now, and there's some results from back in 2007. And what we can see is that APs are getting actually smarter about airtime scheduling. It's a hard problem, but it's improving. We can see that they have different behavior related to assigning 8 stations to different channels. None of that is standardized, right? So it's all secret sauce, and it's the kind of thing where, you know, if you're looking to kind of grade the performance of an AP, it's the kind of thing you'll have to test, because again, there's no definition of how it should work. It's really just up to the implementers. We do see, as we saw today, some cases where the decisions that are made might be questionable. You might wonder why, for example, if you've got 3 perfectly good radios, you end up with a situation where you've got 4 stations all using only a single radio. And one of the things we did notice is that we haven't seen many cases where devices get moved from one channel to another. There could be reasons for that. One is that our tests have been mostly, as you saw today, fairly short. That may be a function of time. Maybe an AP, given enough time, might decide that it's a good idea. But it's also probably a function of the fact that APs are probably fairly loath to move stations, because when you move a station, they will of course lose connectivity during the time of the move. It's, you know, like a roam. You know, that can be quite disruptive, and unless an AP can come up with an extremely good reason for doing it, it may just not. And then, you know, final point, Tim made this as well. You know, these days with the kinds of link rates we're seeing, and the number of devices that are appearing on these APs, you know, given the how many devices are going wireless and what people are doing on them, it's actually fairly important these days to have a high capacity Ethernet port. So something more than 1 gigabit per second. You saw today a number of times that we were able to see over 1 gigabit per second. And, you know, this is the kind of thing that's going to be more and more common even in the consumer setting. As I mentioned, we have all of our tutorials posted. If you go to our website at octoscope.com, you can get this list. But again, just as a reminder, you can see we've talked about OFDMA over here. We talked about multi-user MIMO in here somewhere, I'm pretty sure. If you've got other questions on any of those topics, obviously let us know. I do see something in the QA. Craig wants to know, are there any standards being worked on for band steering or load balancing? Not that I'm aware of. Obviously, Craig, you know better than most that there are protocols to enable it, things like 11V and 11K for sharing information to allow the APs to make some smarter decisions. But as to, you know, standards like whatever you should or shouldn't, or, you know, how it should work, I have not seen that. Probably there will be something in the standards around testing that may take advantage of some of the work that Tim has done here or in other places. And, you know, again, I know, Craig, you're familiar with TR398. That may be something that the Broadband Forum will want to standardize from a testing point of view. And we know that the Wi-Fi Alliance is working on similar consumer experience test plan. And, you know, again, they may be something they cover. But as far as standardization around, you know, defining how it should work, not that I'm aware of. It's the end of the content we have. Thank you all for attending. I know we went a little bit long, but thank you for sticking around. We do appreciate you attending, and we'll see you soon. Thanks.